Hello ladies and gentlemen, welcome to the last video on Unit 5, aqueous chemistry. We're going to talk about the titration and some of the stoichiometry that goes along with that. Usually a lot of this part of it would have us doing a couple of extra labs, but and so that will help hopefully solidify some of the values that you're going on. They are basically a lot of the same types of problems that we've already have done and have had lots of practice with. So let's get started. The process of what we're looking at and where this actually happens, a lot of the solution stoichiometry comes from what are called titrations. And a titration is it's a technique utilizing a burette, usually a burette, to figure out the concentration of a solute in a solution, or trying to figure out where some things are. This can usually be done utilizing your stoichiometry problems, knowing how much of your known that you're adding to it, and the other big part that comes with this is utilizing it within the neutralization, and you look at endpoints. And early in the year, we had talked about doing the utilizing phenolphthalein, and phenolphthalein is a indicator. There are a lot of other indicators. Sometimes even there are indicators inside your home. You can utilize, like, grape juice can be used as an indicator. If you take a leaf of red cabbage, even though it looks purple, you can, if you boil it for a while, you'll actually be able to get that dye, that purple color, to go into solution, and that is actually a very common indicator that some of you may even use for a lab late in class at some point. And so what that does is it gives you an idea of where the endpoint actually is. And so it's a method that we use in the classroom. It is very widely used in a lot of classes that are in college as well. We try to do them at least a couple of them in our classroom, just because it's a good technique. It's a good, useful laboratory tool that we can use. What you usually do is you have a standard solution. Usually that will be what goes into your burette, and then an indicator will go into where you actually don't know, so that you're going to add that. You never, ever, ever add your indicator to your burette. It will ruin a burette. And you have to know what your endpoint is, and the color change is usually that endpoint of the titration. And actually, the tricky thing is the endpoint that you see, the color change, especially with like phenolphthalein, is when it goes from a acid to a base. And it's actually just when it just goes over the top, and it's not a lot, but that's why we utilize this a lot in analytical chemistry, is to grade students on their ability to actually make those last things, is that we will know how much you have in there. And so you're going to have those labs where you're asked to do a titration of you don't know what it is, but the professor will know, and based on your calculations, they will be able to assess you on whether or not you know how and have good analytical skills. That equivalency point is usually what you're looking for. Now, the endpoint is going to be just beyond some of these equivalency points. Some of the easy ones are based on the fact that you have certain balanced chemical reactions. And so we're going to have that. And to actually get this reaction to happen usually means you have, like, especially with like a phenolphthalein, once you have that 1-to-1, it's still going to look clear. But once you get, say, like a 1.0 0.01 moles of sodium hydroxide, which is just a little bit more than the hydrochloric acid, you are actually going to see that pink, that solution turn pink, and that's going to come out. It doesn't take a lot, and that's why it's very, you can't add a whole bunch to the solute, and you can't add to your, from the burette to the beaker or the Meyer flask or whatever you're adding it to. You have to add little by little, especially once you've kind of established where that endpoint actually ends up happening. And you can get, tenths of a milliliter, and if you have really good skills, you can get like half a drops. And it's really I found it fun, but that's just me. Not everybody will find trying to find those endpoints all that fun on there, but it is something that is a skill, and therefore it usually will take practice. And so that's where you kind of look with some of these, and there's a lot of other endpoints. A lot of them are based on pH, but phenolphthalein tends to be the most common one. That's why grape juice or that cabbage juice from a red cabbage leaf, work so well, because they do have kind of a very similar endpoint and kind of where they kind of look at. So let's start looking at some of the stoichiometry, and so when these might take place. As it might guess, that many of these are going to require us to have multiple equations, but we're going to start off with a simple one right off the go. And it says, how many moles of sulfuric acid are required to neutralize 0.5 moles of sodium hydroxide? So it's a neutralization reaction, so we are given a little bit of information to this. So we know the reaction does happen because it is a neutralization reaction. And so if some of you might be able to just scroll back or look, but we're going to actually solve this problem as if we have no idea that the other part was on the other slide, and that we can see that sodium hydroxide being mixed with sulfuric acid. We know, because it's a neutralization reaction, well, that would be aqueous as well. Water is going to be given off, as well as our salt. And now this time the salt is going to be a sodium sulfate, and making sure that we pay attention to our charges is where that 2 comes from, because the charge on sodium is 1, the charge on sulfate is -2. Those don't match up, so we do our crisscross. Now we see this, we have to balance it, and therefore we will put that there, and it does balance itself out with another 2 in front of our water. Now I have a balanced chemical reaction. Now what I have to figure out is, like, I have how many moles. All we're asking for is converting of moles of one thing to moles of another. Very similar to some of the early problems that we did in Unit 4 when we were doing some stoichiometry. And so here, what we're looking at is our given of 0.5 moles of sodium hydroxide. I need to convert that into moles of sulfuric acid. Well, to eliminate the moles of sodium hydroxide, I would need to put the moles of sodium hydroxide on the bottom. Now, where do I get these mole to mole ratios? That's from the balanced chemical reaction. Just like in earlier units when we did the stoichiometric ratio, it's the same thing. The number in front of sulfuric acid, there isn't one, so that means there's a 1. The 2 goes to the sodium hydroxide. Labels and such cancel out to give me the answer of 0.25 moles of sulfuric acid. and that will that's all the answer is. If they wanted grams, we would know how to go there. If they wanted to know what the concentration was, we would need to know something just a little bit more from that as we kind of continue on and get more complicated problems. So these are just that. They are very similar. They're just kind of piggybacking off of ones that that you've done a lot of from previous units. So here they give us a little bit more information, and a 25 milliliter solution of sulfuric acid is completely neutralized by 18 milliliters of a 1 molar sodium hydroxide solution, and they want to know what the concentration of the sulfuric acid actually is. So we have to then kind of, again, balance chemical reaction, which I'm going to use from the previous problem. I'm going to resize this picture here so that I have a little bit more room with that. I then will take my neutralization reaction, which was from the previous one, and since it was from the previous one, I am going to balance it as I write it. So we have that information for us, plus sulfuric acid, aqueous as well, to give us, and then it would be again a water, but although the second part of this isn't really all that important, in this problem there are others that will be more important. And so it is important that we pay attention to when it is important. That's a liquid. I think I forgot to put that on the previous problem. Oh well. So I need to find the number of moles. Well, how do I find the number of moles when I don't have a mass? Remember back that again, we had an equation, so to speak, the molarity is equal to moles per liter. I have a molarity, I have a volume, and the thing is I have that of sodium hydroxide. I also have the volume of my sulfuric acid, but I got to find the number of moles to find the number of concentration. And so when it comes down to, I need to then utilize that bit of information and say 1 molar is equal to, say, moles of sodium hydroxide divided by, now I need to make sure I convert my 18 milliliters into liters. So it's very important that that is done as well. And so I can see that my moles of sodium hydroxide, because of how it works, and it's very easy, a very common concentration for sodium hydroxide is a 1 molar. You'll find as you experience some of the problems, it's usually very rare that it's like 1, 3, 6, 12, very rarely do you need that, but usually like a 1, 3, and a 6, that's usually all you need of a sodium hydroxide. You can get more concentrated if it was deemed necessary, but a lot of times it's not. So we have this here. Now I need to again utilize the mole to mole calculation to convert 1 mole of sulfuric acid, and again the 1 came from the balanced chemical reaction, and 2 moles of sodium hydroxide. The 2 again came from the balanced chemical reaction. And so I can see my couple of these things cancel each other out. To see now, I get a really small number, and you're like, whoa, Peterson, it's a little crazy here. It is a very small number. And that's because it doesn't take a lot to you're only using small concentrations, which would be normal. And so I now have 0.09 moles. Well, How do I get the concentration? Again, utilizing this equation, I can use the volume that I have up here. And I just need to make sure that I convert that into liters to find that I have a concentration of 0.36 molar sulfuric acid. So that's what we end up doing. And it's actually the only weird thing is just how we convert to moles. Doing the stoichiometry isn't actually all that difficult. We can even calculate other things from that as well as we continue on. Now the next one, how many grams of calcium hydroxide are needed to neutralize this? So here they're asking you how much calcium hydroxide did I add to the solution? And so this one will require a little bit something else. It's a different problem, so we're going to have to write out that chemical reaction a little bit differently. Still a neutralization reaction, which is very nice for us. And that I have my calcium hydroxide, which again is going to be 2. That 2 came from calcium because the charges don't match up. And that will be aqueous plus nitric acid, HNO3, aqueous, plus, oh nope, not a plus, wanted to get continuing on, is going to give me water, which is a liquid, and in this case it will be a calcium nitrate. And again, because of paying attention to my charges, I need to have the 2 on the outside, and that will also be aqueous because of rule number 2 as well. When I look at balancing it, balance out your salts first, and in this case it's going to be a 2 to go there, and then to balance out my water, a 2 goes there. So pretty easy in that sense of how that all works. Now I'm going to resize this to rework some of the problems as I'll need to. Now I have it here. There's going to be some things that again I need to calculate. I'm going to utilize again my molarity is equal to moles per liter. Because I have that of nitric acid, that's how I'm going to calculate the number of moles that I need, or how many moles of nitric acid I have. And so from there, I'm going to go 0.1 molar is equal to, and again, we need to convert my 25 milliliters into liters, and nitric acid, and 0.025 liters to give me a value of 0.0025. So we got even smaller again. 25 moles. Now that I have that, I can utilize stoichiometry, that stoichiometric ratio that we've been working and dealing with, and that I'm going to then utilize my 0.0025 moles of nitric acid, converting that to I'll eventually want, and that will be a 2 came from the balanced chemical reaction. 1 mole of the calcium hydroxide, that came from the balanced chemical reaction. Now that I have that, my labels can cancel off. to give me an even smaller number, which I know is just like crazy time happening here. And we get equal to 0.00125 moles of calcium hydroxide. Okay, but from there, now what we have to do is I need to convert that value into grams. And so, but how do I do that? How do I convert moles of calcium hydroxide into grams of calcium hydroxide? I have to use the molar mass. Calculating that molar mass is still just such an important part of what we do. So I need to calculate the molar mass, which means I need to find calcium, I need to find oxygen and hydrogen. 2 times 15.99, 2 times 1.01, 1 times 40.08. All of that added up together gives me 74.08 grams per mole. I take that value and I'm going to multiply it by the number of moles over there, moles there. Moles cancel out to give me an answer of not very much, 0.93 grams of calcium hydroxide. So that would be about as complicated of a problem we could have. Could be maybe a little bit more complicated, but that's why you have multiple things of homework, different problems, and why we have recitations so that we can ask questions in more of a face-to-face time. So with that, we end our discussion on aqueous chemistry. We will still continue to use aqueous chemistry and all the skills that we've learned from this unit and the previous unit, and we will add those on into the next unit when we start talking about thermochemistry, and when we we'll also make sure that we'll utilize what we've learned here and add that into the lab. So until next time.